And it looks like we're live. Welcome back, everybody. My name is Nico, and today we're gonna take a look at Minecraft save files. We're gonna reverse engineer. Well, not really reverse engineer. It was already reverse engineered before, so we're just gonna look through the knowledge people have gathered on Minecraft save files. You can take a look at the binaries and see how the files are, how the data is stored, and all of this we're doing for just so we understand how essentially every single block or in a chunk is saved in a save file, right? Reason why I'm started looking into it is because I actually have a very large world. I think it's about 30 gigs, and it used to be a save file from a large server, and on that server there is a few places that exist that me and my friend would like to visit, but because we don't really know the coordinates of those places, I came up with a thought that there's probably signs that people place naming the places that they build. So if my idea was, if I look through the save files, if I look through the signs, Minecraft signs in the game, I might find where the signs are located and eventually find the places, if that makes any sense. So some sparkling water with me today. So yeah, that's kind of like that's the main idea here, is to look through the save files, see if we can decode the data. It's not like it's encoded or anything, but it takes a few steps to get to where we can see the raw bytes and bits of everything. So what else? So yeah, that's pretty much it. Looking for specifically Minecraft signs, but I'm pretty sure if you're looking for like a certain type of block, you might be able to come across it. So we'll do two parts to this live stream. The first part, I kind of know everything about how to get to the MBT point, but I've never actually tried to break down the NBT data and look at how everything is packaged together. So we'll see how it goes there. So the second part is going to be a little bit of a learning for you and me, for both of us. But the first part is pretty easy, pretty straightforward. So we're just gonna go through the first part very quickly, and yeah, that's pretty much it. There are programs that do that kind of stuff, that like what I'm looking to do, like NBT World, NBT viewers, readers, wherever. But what I need to do is I need to write a program that looks for one certain thing, because an NBT, like if we use an NBT viewer to kind of give us a list of everything, and there's not really a way for me to animate that. So I have to write a custom piece of software that will open up each region file. We'll get into what the region files are in a bit, but I'll have to write a program that opens up each region file, deflates or inflates all the chunk data that's been NBT chunk data that's been not compressed but deflated. So you'll see what I mean once you get there. So it's a multi-step process, but it's pretty easy, pretty straightforward. Is there anything else to talk about? So yeah, like I didn't want to use others people's software because it just doesn't fit the tasks that I need. So the task that I need, like I said before, is just we need to look through the files, through the game data, through the save files, and try to find signs that have words or strings that we're interested in. So, and compile a list of those words and their locations as well, like where the signs are located. So the software I'll be writing at some point in the future, not during this live stream, but at some point in the future, is gonna be just gonna be doing one task of extracting that information from the save files, and because it's a one specific purpose. I'm not trying to write like a versatile software, just one specific type or one specific like with a software with one specific purpose. That's all it is, and I need to make it as efficient as possible so it doesn't take 2,000 years to run, and I need to make it friendly such that friendly like in a way such I can reuse it later on, or my friends can reuse it later on, or maybe if people online also wanna use it, maybe they could use that as well. So but we're not there yet. Let's start before we start writing software, before we start writing custom software, we need to kind of play with sticks and stones here. I don't know if that's the actual expression, but kind of need to go down and do everything by hand first to understand how to do it. How to tell a computer how to do it. So that's what we're gonna do. So like I said, we're not gonna be doing like an actual reverse engineering because everything was already reverse engineered before us, per se. So we're just gonna go through the knowledge that has been collected by people over the years. This specific article dates back to 2014, but it actually goes back even further. Like they just made some big changes in 2014. So yeah, a good like 3 good places to start before you kind of start doing anything is to actually read what you're working on. So we wanna look into the save files of the world and see if we can find like what we're looking for, right? So the 3 helpful, very very helpful actually places I found is on Minecraft Wiki. You have a couple of pages here. So the region file format, which actually describes how things are coded in not coded, but how the binary looks like, and how to get what you're looking for from there. And then you have some general chunk information. I've never read this specific page, but I think it has some pretty good stuff. Like there's all those diagrams here, which because I didn't read that, I'm probably missing out on a lot of good information here. But I actually just found it. So if you people want to do your own experiments, I suggest you also take a look at this chunk page as well and read through it very carefully, because I think it has good information. But I was basically going off of these 2 pages here: region file format and chunk format. Chunk format's basically once you get to the NBT, and chunk format is stored in the NBT kind of format. But before we actually get here, we actually need to get here, right? So this is why we start with the region file format first, because all of the you'll once you get there, you'll see how all the data is encoded. Yeah, I guess I will say that. In terms of tools, I'm going to be using Hex. This is a Hex editor, Hex viewer, so it's a Hex hexed.it, so it's hex edit essentially. And this just allows me to see all the binary stuff that I need to see, and then we'll be able to go in and break that down. So what do we have here? We have our subject. Now I have this folder here. I just kind of have a whole bunch of stuff in here. We'll take a look at all those things later on. But if you, just like me, starting with a like, in order to do the experiments, you need to have a world, and I've created essentially a testing world where what I've done, I've placed a sign. I know exactly where I placed it, by the way, just because it's an experiment, and we need to have one variable that we're playing around with, and then everything else needs to be pretty constant. So I know what I'm looking for. I'm looking for a sign that says hello, that is located at I have some I don't know if you can see, but I have the targeted block, so I know where it's located, XYZ. I also know what kind of block it is. It's an oak sign, and I have the related chunk information that I actually need to know. So I have the chunk location, so -13, 4, -1. By the way, I never figured out what the 4 stands. What's for the 4? It could be something, but I just never really came across any explanation of what that is in the documentation that I've read. And then you have pretty important piece of information here, which tells you where is that chunk located. So this chunk, this -13, -1 chunk, is actually located. It's numbered 1931 in this region file. So basically the way it works. I'm gonna pull out my whiteboard here. So each chunk is 16 by 16. Actually, let me zoom in a bit here. So each chunk is 16 by 16, and again, I'm not gonna go into too much detail. There's it gets complicated, but the way the chunks are saved is it's not one single chunk in a save file. It's actually a whole bunch of chunks inside of one file, which is called a region file. So you'd have multiple chunks, however many. There's some math behind it. As far as I understand, if chunks get too heavy, when there's too much data in the chunks, they actually might become a part of like a different region file. So, but that's how far my understanding goes as of right now. But I don't know if that's actually the case. I haven't proved that or haven't experimented with that. But we'll see. We'll start with the basics. Okay, start with the basics first. So we have all those chunks, 16 by 16 block chunks, saved inside of a region file. Region file, I'm just gonna put it as a r dot, and it's I'm just gonna try and draw a little file. Does this look a file? Doesn't matter anyways. And so basically what that region file consists of, it consists of two tables and a whole bunch of data. So the table, so the whole, if you imagine the whole file, region file, we're gonna have essentially two. It's two or is it three? Let me remind myself. It seems like so there's essentially there's a table here. Yeah, there's two tables and then a whole bunch of data after. So you have one block, a second block, and then you have some unspecified amount of just data, like large block of any size, essentially, depending on how many chunks you have and stuff like that. Again, as far as my understanding goes, this first block has some data. So what do we have in that first block? First block has our locations. Second block has our timestamps. So locations. Just gonna put locations, and then I'm gonna put time, and then here I'm just gonna say chunk data. And so basically this is a table in this first part of the file, which goes from address 00 to 0FFF. Should I put that on my little yeah, let's put that here, 0 to 0FFF, and then this one starting from 100. This is all hexadecimal, right? So 100 to 1FF. So you'll notice that the size of this chunk of information, the size of this chunk is, if we pull out our calculator, this is 1,000, right? So this is starting from 0 to FF, not 1,000. It's a hexadecimal 100. So I should correct myself. So hexadecimal 100 is 4096. So the size of this is 4096 bytes, right? And this is also 4096 bytes, and then this gets as big as it can get. So 4096 bytes, that's equals to 4 KB bits. So I'm just gonna put it as a kib. So it's KB bits, meaning that it's 10 to the power of it's 4 times 10. The way I wrote this may not make a lot of sense, but it's 4 times 10 to the power of 24. And let me just quickly double check my math here. 10 to the power of 24. No, not square root. 10 to the power of okay, whatever. I'm just gonna do it in the Google here. 10 to the power of 24. Or is it 2 to the power of 24? Hold on. Okay. KB. I didn't study for my I didn't study for this educational live stream. 1024 to the power of yeah. You know what? Yeah, just this is what you need to know right here. I know where I was going with all this crazy stuff. All you have to know, this is 4096 bytes. It's just 4 kibibytes, kibibytes, yeah, not kibibits. So and then each chunk of the file has a table, and then we'll look into the tables in more detail here in a second. And then the time chunk also has a table. Now I'm not gonna talk much about the time here, because time is because of what we're really interested in. Time really doesn't matter. Time basically contains information on when the certain chunk was modified certain Minecraft chunk was modified last time. And then we have chunk data. So I'm just gonna say Minecraft. Minecraft. The reason I want to say Minecraft is because I'm talking about the chunk of the file here. That's not the same as Minecraft chunk file. So I just want to be clear with that. And this is just and whatever is in here, this is just a bunch of it's not a table, it's just data. So it's like wherever, just bunch of bytes. So this first file chunk, that this location file chunk, what does it tell us? It tells us the offset in the file where the information for our chunk is located. So let's go back to our origin file format here. So this is what we talked about just now. You have a whole file. Your whole file is divided into two tables, and then the chunk space as big as it gets. This is the first table, the chunk location. So you really have 3 bytes here that you care about, which give you the offset. So in this table, let me see if I can put this in nicely. So you would have essentially 2 pieces of information that you're interested in. The offset, and then the last thing you have is a sector count. Sector count is not it's not useful, so I just we're not really gonna do much with it. So I'm just gonna say sec count. What's up is the chunk. So the timestamps. Timestamp table is pretty easy. You just have four bytes, which are just telling you the time when the chunk was modified last time. So I'm just gonna keep this nice and simple. Put just one table. And then I'm just gonna put time. And like I said, for this last part, it's just a whole bunch of information. So this is kind of like the theory on the whiteboard. How about we just go and open up a file and take a look at what we're working with. So when it comes to when you open up your world file, this is what you're gonna see. You're gonna see all those files here, and data, advancement, data packs, whatever, entities, players data. What you are interested in, you're interested into the region folder. This is specifically for the overworld. If you're interested in working in the nether, for example, the nether dimension, or if you're interested in working in the end dimension, you have these folders called dim1 and then dim-1. And if we go back to this region file format website or the wiki page, you'll see it'll tell you what if depending on what you're looking for, where you're gonna find it. So we're interested in the overworld, so we're gonna look inside the region folder. In this region folder, what we have is a whole bunch of files. So because this is my test world, it doesn't have a lot of region files. It has a very small amount of region files. I didn't really run around much, so it didn't generate a whole lot of stuff. But if you're playing on a big world, a big server that has people been everywhere within a certain border limit, then you're gonna have a whole bunch of those files. It's gonna add up to 30 gigs pretty easily. So yeah. In regards to the MCA files, so maybe some of you probably have heard of Minecraft Anvil format. So it's kind of like MCA. That's how you know that's the Anvil format. I want to see if there's if it mentions somewhere in here. Yeah, so this is this Anvil file format. So MCA. I'm assuming MCA stands for the Minecraft Anvil. Yeah, the Anvil file format may changes only to the chunk format and change the region file extensions from MCR to MCA. So you have MCA files. You know that's your chunk format, your Minecraft Anvil file format. So if you're working in the older versions of Minecraft, things might not work. Things might be different, right? So, but you know, I'm pretty sure nowadays everybody just works in a this region formatting hasn't changed a whole lot over the years, so it's, my understanding, it just stays pretty much the same. So, but regardless, let's not dwell on this too much. Like I promised, let's go open up one of our region file formats and or region files. This is where if you don't know what region you're looking for, like say for example, like in this case, I know what the region file that I'm looking for. Like say for example, you know what chunk you want to look for. Say let's just use -30 and -1, right? So I want to look up the data for -30 and -1. How do I do that? Well, if you don't know which region file this chunk information is saved in, there's some math you can use to figure out where in which region file it's located. Now, it's a simple math, so I don't really care about going too much into detail of how it's done and stuff like that. There's some code here which looks like there's like some C code, and then there's some I don't know what language this is. Is it Python or something, or maybe it's some Java or some other nonsense. But again, depending on which programming language you use to program your stuff, or even if you just calculate it by hand, you have all the information you need to calculate where your chunk is, in which region file your chunk is located. There's some noise in the background right now, but just let's ignore that. Don't worry about that stuff. It's my neighbors. But in this situation, because I don't want to spend too much time looking at the math and stuff like that, I'm just gonna take the information I already know. So I know that the game tells me that this chunk, this -30 and -1, is located in region file -1, -1. So if we go open up our, I'm just gonna open up the folder here. So we actually have this right here. So our region file -1, -1. If you have some other chunks somewhere else, you would have some other chunks saved in some other files dependent. So, and they're all you'll see that they're all different sizes. So depending on how much stuff you have, your file size would change. So let me drop this down up here. So here we go, here we have it. So first thing you see is you see a pattern. When we open up the binary file, we're not seeing a mess. Like, we're not seeing just random bytes and bits everywhere. We're seeing some patterns, some nice little, straight lines. You can see that this is organized in a way. And we're gonna figure out here in a second what way it's organized in. This is actually what the table looks like when you break it down into the essentially the binary format, right, on the binary level. So it starts, our first table, like we talked about before, our first table starts from 0, 0, and it goes all the way to FFF. So if we have in this hex editor, we have the ability to jump to any address we want. So if we type FFF, it will take us to the end of this first table. So this first chunk of the file ends here, ends at this address, and we can see that. So this is first table that has all of our world offsets, ends here, and this is where our this is where our second table begins with our time stamps and stuff like that. So this thing right here, okay, and then it goes all the way to 1, because it's 100 in size. It goes to 1FF, so we just add 100 in hexadecimal. Or if it makes more sense, I can quickly do it in normal decimal system. So if our address is first, let's convert it to sorry, wrong place. So if we take whatever we have up here, our address, our first one starts from 0 to, and it goes to FFF. You'll see that it's from 0 to FFF, it's 4096. So that's your 4 kbit sized file chunk. Now if we add a 1000 hexadecimal on top of it, so if you add another 4095 starting from was it like 1000, that's gonna be another 4 kbits. So we'll take that, put 100 because that's the size of our chunk. That takes us to the 1FFF. This is the end right here. By the way, something is burning in my apartment, or my neighbor's apartment. But by the way, if you're not familiar, like many people are probably aware of how this how this thing works. But if you're not someone who's familiar with, on what I have up here on the left side is the address of the byte. So it starts with 1FF0, F1, F2, F3, F4, F5, S6, F7, F8, F9, FA, FB, FC, FD, FE, and FF. So that's because it's all hexadecimal. That's kind of how it looks and how it works. Again, if we would do something like, let's take a look at 200 hex. You would have this would be your 2000. This would be 2001, 2002, 3. And then, I don't know, like you want to see what 200, I don't know, C. It's right here, right? So, simple stuff. Again, many people already know that, but for those who may not be familiar with that, that's why I'm kind of stopping by and explaining that. So this is where at address 1FFF, our second chunk, our second table chunk of the file ends, our second table ends, and this is where the gambled mess begins. This is where we're starting to see all those data, and this data doesn't make sense, and whenever we see data like this, we usually just assume it's encrypted or encoded into something, but what actually happens here is this data is I want to say compressed because a lot of people would understand if I say compressed. However, it's not technically compressed because compression usually is a little bit more. It's a little bit different. So what's going on with that file? What's going on with this data? This data is deflated. So originally, you had some data. I'm just gonna talk about deflation here. So you had some sort of data here, which was of this size. I'm just gonna draw a bunch of squares, and then you deflate your data. You essentially compress it, but it's not compression. I'll talk about why it's not compression in a second. So you make your data smaller to save up space. Otherwise, we would have our Minecraft worlds would take gigabytes and gigabytes of space. So it's compressed. It's deflated. For like a better word would be deflated. Now the process of taking this data and going back to the original is called inflation. So you deflate something into smaller space requiring. So let's put it this way: you have a certain amount of data that takes up space. You deflate it so it takes less space. You have data that takes less space. You wanna use it. You have to inflate it in order to be able to work with it. Now, reason why this is not called compression is because when you take data and you compress it into something, there are some header files, or not header files. Sorry, I'm a C programmer right here. C programmer right here. There is some header bytes that gets attached to your data. Should I? Yeah. So I will talk about this in a second. I will talk about all this stuff in a second. But we have a standard RFC 1950 which talks about the zlib compression format specification. And just to very quickly go through it, what we have here is we have compressed data. So it's a data, it's a deflated data that gets surrounded by bytes. So we have, bytes like this, byte like this, 4 bytes of other information, and it gets another 4 bytes then. So you take your data, you take your compressed data, essentially you take your your deflated data and you wrap it up in some extra bytes, some extra information. Now the reason you want to do that is because in those extra blocks up here, you're gonna have information such as compression method, like how much it was compressed, some flags as well, and at the end here you will have things like your CRC, so your checksum, essentially data loss prevention measures, right? And if you really are interested in knowing all that kind of stuff, you can read into this text file whenever you have time and look at all the different header data that's being attached. So it's called, some people call it a wrapper, some people call it a header. I just call it header, bytes, wrapper, wherever. So deflated data gets wrapped up with some bytes, and this is what compression is. Compression is something that deflates your data and then it attaches some bytes. It wraps that data with some bytes. Again, the bytes, there's compression method, some flags. Compression method, this just explains in detail. Compression information, some extra, like, you know, you have dictionaries, compression levels, because you can really squeeze the data down, and you have the checksums as well. So your data loss prevention measures, simplistic ones, right? Now, all this, to attach those bytes, you have to have extra processing power. You have to essentially, like, your CPU would have to spend some time actually calculating your checksum, you know, attaching all that information. For all the chunks that you have in a file, that would be pretty much the same. So the developers behind Minecraft, they decided to just deflate the data without compressing it. So they deflated the data without having those without having have to deal with those extra bytes on the wrapper, like on the header and the footer and stuff like that. So the data they have, the chunk data they have, it doesn't have you know, checksum. It doesn't have compression flags because it's all compressed the same, and it would take a lot more computing power to calculate the checksum. So they just said, we're not gonna do it, you know, because it doesn't really matter. So if your world does ever get corrupted, that's probably why, because they don't have those checksums and wrappers. But checksum doesn't really fix anything. It just tells you that there's something wrong. As far as my understanding goes, I don't know. I went to computing school a while ago, so I don't remember stuff anymore. So anyways, this is where our data begins, and this data can go and go and go, like, for a while. And I'm just gonna scroll it through quickly so you can see the chunk, the file chunk. So boom, ends here. Then we have a bunch of zeros. It's gonna be like that for a while, and then boom again. This is data for another chunk, and then again data, 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 bunch of zeros, and then next chunk, the data for the next chunk. Something you'll notice is everything, all the data for each chunk is aligned to 100 hex. So if I go back in here, the way I kind of drew this might be a little bit confusing, but if we take into that, if you look into that Minecraft chunk data, all the data, let's just draw another one here. I'm just gonna type it because it's faster. Minecraft chunk data. Okay. So you would have your, we already talked about the two tables. Then you're gonna have your, after those two tables, I'm just gonna draw it like this. This would be your 1FF. And then here you would have something going like from 2000. This is your data for your first chunk. This is your data for your second chunk. I'm not drawing them equal size, but they are equal in size. And then you have your next chunk, and it goes on forevermore. But so let's not rush here. So what basically what happens here, you'll see that there's a lot of empty space right here. So you don't have data occupying the whole chunk. everything just gets aligned to 100, essentially to the to the certain multiplier of 1000, in order to make it easier for the program to read it. It's just when you have everything aligned nicely, it's just easier to work with data like that. Okay, there's surely a lot of empty space that's being wasted here, as you can see, but the reason we don't use that space is because it's just gonna be a heck of a pain to try and use this space. So we just align everything to 4096 bytes. You know, you have 4096 bytes per each file chunk. That's what we work with. Now, as far as my understanding goes, if the chunk's data size, the size of data exceeds this space, what's gonna happen? It's gonna get assigned two chunks. So, say if I'm building a lot of stuff, and my deflation doesn't work, like, or it's not that it doesn't work. My deflation is not able to compress it into this chunk of 4096 bytes. Then it's gonna give then the game will give my chunk two chunks, right? That's as far as my understanding goes. So, but you can verify that yourself. Does it really matter? Well, if you're working on a big, I haven't really encountered that yet myself. Like, I haven't seen a place where a chunk would take two file chunks right here. Like, Minecraft chunk would take two file chunks. So, but I'm assuming once I start working with bigger worlds that have like 30 gigs worth of stuff, I'm assuming there will be chunks that they just take a lot of space. So yeah, but I'm just letting you know, if you again, just go read on the Wikipedia. Don't just trust me here, but that's my understanding, and I'll if I'm wrong, I won't be able to correct myself, unfortunately. So I can't go back in time and fix this live stream, right? So what else? Let's go back here. So this section here, the payload, that's what we just talked about. So all this stuff up here, this is the payload. This is what they refer as payload. I refer to that as Minecraft chunk data. The same thing. And we should probably not rush into breaking this table down. I want to go back to our first table. Our first table here. Let's break it down and let's find where things are. So, what do we know about our chunk that we're looking for? It's -13, -1. Now, like I said, in this big file, we want to know which one of those data chunks has the information for our specific chunk. How do we know that? That's what our first table tells us about. So our first table will have an address offset. So it will give us a number. It will tell us, okay, take this and multiply by 1000, and it will take you to wherever you need to be, right? So, or actually, sorry, there's no multiplication. We're not multiplying anything. Sorry about that. No, there's no multiplication. It tells us the offset. We just go to that offset, right? Or was there a multiplier? we'll get there. We'll get there. So in order to find your chunk, so in order to know the offset of your chunk, you first need to find it in this table. In order to find it in this table, you need to do calculations. So now the calculations you do in order to find that information is there's a formula right here. It's 4 times blah 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 blah. Sorry, this is actually not the right formula. This is the right formula, the one that has modulo. So you guys, if some of you don't know modulo operator just basically tells you the remainder of division. So say if you divide like 10 by 3, it will give you like a remainder of 1, right? So because you have 3 times 3 is 9, and then you have 1 left. So that's what modulo is. So if you do like 10 mod 3, it would give you 10 modulo 3, it would give you 1. I did some calculations here that I just want to quickly go over just to show you how it's done by hand. You don't have to do it by hand. You we have computers, so you can literally just do like you can go online and you can type modulo calculator. So and it will take you to whichever website. So say you want to find like for example here we're dealing with our x that we plug into this formula will be -13. So -13 modulo 31, you calculate that, gives you 18. That's the remainder of that operation. Oops. So let's quickly go over this. I actually made a mistake in my calculations at some point because the way things work in Minecraft, the way the axes are defined in Minecraft always piss me off, because they have x, z, y, because you have your x, you have your z, which goes sideways, and then you have your y, which is your vertical thingy, your vertical axis, which is like if you work in any other piece of software, it's usually x, y, z, whereas your x, y is your your horizontal axis, and then your z is your vertical axis. So just a reminder, I guess, to be careful here when you plug numbers into the formula, because I spent a good amount of like a good 30 minutes trying to understand why is my answer is wrong. It turns out it's because I was using 4 initially in my formula, and that's not the right number to use. You have to use -13 and -1. So if you do your modulo calculations, you eventually end up with this number here, which is 0f48. So you'll end up with this decimal number that you can easily convert into your hexadecimal number. So f48. That's the I shouldn't really say offset, because this is I said offset, but I don't want to confuse people, because this is offset within the first table, whereas this offset up here is a different offset. That's the offset within the whole file. So just ignore this offset, like where it says offset, just ignore this one up here. We'll get to this offset in a second. So all these calculations give us one hexadecimal number, f48. That's our address in the table, in the first table. If we go type this f48, this will take us down to where all the data in the first table for our first for our chunk that we're looking for is located. So there are four bytes that we're interested in. So chunk location, 4 bytes. So we have 0, 0, 0, 0, 1F, 0, 2. So what this tells us is that our offset is 1F, but our sector count is what is it, 0, 2. Again, like I said before, sector count, I don't really know what that is, and it's not really important. So I never really cared about sector count. If you really do want to figure out what it is, go ahead. I think for most of them it's sector count is gonna be 0, 2. This one has 0, 1, but yeah, who cares? What we do care about is offset. So this first table, by plugging this number, by plugging the address we calculated in this using this first formula up here, we now know the location. This took us to the location of the information that contains to the location of the information that tells us where to find our chunk data. So it tells us 1F. If I go back to here, you'll see that I kind of broke this down already. So we have the offset 0, 0, 1F. Again, if you're working with a file that has a lot of chunks, or has a lot of large chunks, you probably end up in a situation where you might have a pretty large offset. But right now it's a new world, doesn't have a lot of stuff going on, so there's only 1F offset. I don't know why I said chunk length in here, because I don't think that's chunk length. I think I confused that with something else. Like I said, like we just saw, this is a sector count. This is not. This doesn't have anything to do with the chunk size. Oh, actually, no. Never mind that. Sector count. Remaining byte that gives the length of the chunks. The length of the chunk, also in 4 KB sectors rounded up. Chunks are always less. So that's some data that you kind of have to think about. But again, it's not really important. So let's just focus on what's important, which is this address up here, 1F. And the way we figure out where all the chunk data is located, we take that 1F and we multiply that by 100 hexadecimal. So we take that 1F again. If it says 3C, you just do 3C and you multiply it by 0, 1, 0, 0, 1, 0, 0, 0, which is going to be 3C 0, 0, 0. It's a simple math right here. This is why it's nice to have those empty spaces in the file, because everything's gonna align so nicely that you have really easy numbers to work with. And if you write in a software, it's just so much easier to do that, because everything is straightforward, everything makes sense. So let's go and let's go to that address. Let's go to 1F000. And this takes us right into the beginning of where our chunk data begins. This the chunk data for the chunk that we're looking for. So this is data for -13, -1 chunk. We calculated again, just to just to go over everything again. In the first table, we know our x and y of the chunk that we're looking for. We're using the formula provided here. we calculate the number in the table, in this first table, the address in this first table, I should say, which was was F48. Yep, F48. Now looking up in this F48, it gives us the address where we can, or it gives us the offset where we can find our data for that specific chunk. If you want to do it for some other chunk, like for example, let's just do a very quick and easy example here. I don't know what chunk this is, but there is 6 and 7, 9. So I know that if I type 6, 7, 9, and I do 0, 0, 0, that should take me to where the data begins. Now this is actually a really good example of what I said earlier, with some chunks are taking like much more space than other chunks. So like for example, in the earlier example, we've seen a bunch of zeros just before the next chunk. This chunk, the chunk before that just happens to be so big that it fills up the whole block. So that's why we end up here. And that's why it's all like tightly packed. And I know that this is, I know for example that this is a new chunk because address, again, you have the address and then it starts with 0 as well. But it doesn't always start with 0. Let's look at something else. Like we have some stuff up here, maybe like 698. Like this seems like a nice little chunk up here. 698. 69800, I should say, because this is hex again. Pretty. Wait, didn't we just look at that one? Anything else? Just anything random? Okay. Like this chunk, for example, 1, 0, 2. So do 1, 0, 2, 0, 0, 0. Again, this will take us down. The offset will take us down to where the data for that specific chunk begins. If you wanna, I don't know, some other chunk, just one more example. So like, for example, for this chunk here, which is again some other kind of chunk, I don't know, you would have to do reverse calculation to figure out what where it's actually, I don't know, can you even calculate it? Probably somehow. So if I want to know where the data for this chunk from this table is located, I just go down to 640 0 0 0 0, and here we go. That's all the data for that specific chunk. Now I want to just go back to our chunk, because I think at this point you guys already understand the basic idea of how this works. So let's look at the data we're working with up here. So this is where we're gonna get into the payload section and talk about the payload. So payload has the first 4 bytes here of the payload tells us how long our like essentially how long our chunk is, like how much space it takes. So for example, we have 11D3. So, and then we have some other information here. We have like another byte for the compression type, and our actual data begins from here, where it says 78. This is where our data begins. These 4 bytes are a flag, not a flag, but just information about our chunk. This is the compression type. It again, deflation type, I should say, not compression. I know they say compression here, but it's deflation. So this is deflation type, and the actual data begins here. So from this address, let me just deselect all that. From this address, which is currently we have current address is 1F005. Let's put that into our calculator. We're gonna calculate the end of this chunk data. Where is it located? So 1F005, and then we're gonna add the number that's up here. So it's 11D3. It will give us 201D8. 201D8. And it took us right to the end where our data ends. Now, I don't know exactly why it's not exactly at the end. It seems like there's always this 2 zeros at the end, and I don't really know why when you do the calculations it takes you up to here and not up to 15, but it does that. So does it really matter? Probably not, because we're not messing around with things too much. We're just trying to decipher the data here, right? So that's all we really need to know here. Like, we don't need to know anything else really. So we need to know that this first 4 bytes tell us how big this chunk is, how big this file chunk is, and then this is the compression type. So the compression type is always gonna be the same, except if somebody went in and messed around with the game code, and instead of saving it as JLib, which is not JLib, ZLib, which is the default is always, it seems like the default is always 2. It's always gonna deflate it into in accordance with the ZLib standard. But it seems like in some, like for example on a server, they might be able to have another like number in there, like 127, which is like FFF, right? Or FF. Oops. So yeah, no, sorry, not FF. It was just 1F. Nope, not 1F. What's 127 again? 7F. Here we go. So if you have 7F, if you ever see in this 5th byte of your chunk data, if you ever see 7F, that you know that's your custom compression algorithm. If you have 4, you know that's LZ4, which is wherever. Apparently you can modify that in server properties, so you might come across that stuff. If you see 03s, it's gonna be uncompressed, but you're probably gonna be able to tell that it's uncompressed because you're gonna start reading. You're gonna start seeing readable things up here. You know, things like actual words, because once you get down to NBT, you'll see stuff like that. And then, you know, like I said, 2, value of 202 is the default. So for the most stuff, like so far I've seen every chunk has 2, and that's the deflation algorithm used there. I've never seen, yeah, like they say, unused in practice, JZip or gzip. That's you know, you're very unlikely to come across that. So what else should we talk about? But I guess that's pretty much it. That's how you find your actual chunk data. So if you select all of this stuff up here, I'm just gonna, I just wanted to scroll down to show you that this is like one whole complete chunk, and again it ends at the address that we calculated right here, but I'm not gonna include those two of those 0 bytes because it's just, I don't think they're necessary because I haven't seen anything, you know, break because of that, because of not including that. So we can select all those bytes, we can select all that Minecraft chunk, deflated Minecraft chunk data, and we can choose to export it to a file. So we can, if you ever want to save that, you can save it on your for yourself. So for example, like what I like to use, I like to just do like c dot -13 -1, that's our chunk location dot what format is it? This is in because this is compressed as a zlib, I like to save it as a zlib, but you can literally name it as wherever, it doesn't really matter. So I'm just gonna save it on my desktop. Yeah, that's your compressed Minecraft chunk data. That's how you find it. Maybe since we have time, maybe we can take a look at the second table where it has the time related stuff. So most people probably not going to be interested in that because this is just for record keeping. The time doesn't really tell us much. Like, it tells us when stuff was modified, but that's about it. So from my understanding, so we calculated f48. This is the number that we calculated to find our offset. Now, if we take that number and we add 100 to it, which should be like a simple math, but I'm still gonna use a calculator to make sure I do it right. So we take the f48. So 1f48. That should take us, so you just add 100. That should take you to where in the second table you'll find information about when this chunk was modified last time. So again, this is for people who are following the documentation. This would be under your chunk timestamp section. So the way the data is formatted, it's a big endian formatting. So meaning that the way you read it, you read it from the most significant to least significant. Big endian. It would be probably easier if I show some kind of picture here for you to understand. So like we have the data 1 2 3 4 5 6 7 8. In the big endian, that data would be split into like 1 2 3 4 5 6 7 8. Little endian, it would be split into 7 8 5 6. So it's just essentially you're reading from the most significant byte to least significant byte, or for the big endian, and for the little endian you read from the least significant byte to the most significant byte. Now why do I tell you that? Is because that does matter. So in here, in this hex editor, we have the ability to read our data that we have up here. So like for example, if you want to know what time this chunk was modified at, you need to convert this hexadecimal numbers. There's four hexadecimal numbers, 4 bytes of hexadecimal numbers that you have to convert to a timestamp. Now, like I said, this is saved as a big endian big ending right here, big ending integer. So in order for us to correctly read that, we don't read this in little ending, we read this in big ending. Now what this is, this would be, so because it's 4, because this is 4 bytes, this is gonna be our 32-bit integer. So this first byte is 8 bits, second byte 16 bits, 24 bits, and then 32. So this number right here, if you take that number, you do epoch time converter, you take that integer, you put it into epoch time converter, you convert this to a human date, it will tell you that this was Tuesday, or let's look at my time zone. It was Monday, April 22nd, so a week ago from now, I think. Yeah, a week ago from now, I think, at about 8:40 p.m. I mean, so you don't actually have to like do that. You actually do have like a Unix stamp conversion in here already. I just wanted to show you how, in case if you're working with a hex editor that doesn't have the ability to show that conversion, how you can find that information by using just the integer. Right. So again, this one tells me not in my time zone, so that's actually the difference. Or this is where you have to be careful with those things, because this tells you universal coordinated time zone. So it was April 23rd in the universal time zone when I last modified the chunk, but it was April 22nd when I in my specific time zone in Alberta when I modified it. So that's the difference right here. So yeah, pretty simple stuff so far. I hope it all makes sense for you. Realistically, nothing hard up here. Where it gets hard is the next step, the deflating stuff. Because actually, this only took me like 4 hours to figure out. Just playing around with it, experimenting things, and but decompressing things took me a lot more. Instead of opening up this file, I'm just gonna open the file I already have saved. I have it saved in this dissect folder, so let's take a look at this. So this file has all the data. It doesn't have those 2 zeros that we talked about earlier. So this file has only the chunk, deflated chunk data. So now where we go with this is our next step would be to deflate or inflate this data. So we want to go from a little square, we want to go to a big square, so we can work with because working with a big square is easier, right? Because you can't read any of this stuff. So yeah, this is actually where it gets really hard, because this is not data that you can just go and decompress anywhere. This is not the data that you can go and inflate, with your RAR or your 7-zip. It's a lot harder to deal with. You actually kind of have to feed it into the. You have to write some code. You have to use some libraries, deflating libraries, compression libraries, to convert this data from this deflated format into a full format, and that's where we're gonna go next. So let me open up my Visual Studio, and what I did here is I kind of started writing a piece of software that uses existing C code that somebody else wrote before. So if you search up online about zlib, zlib is been used for past 3,000 years. Jesus himself was using zlib to compress his files on Linux or on Linux. So, and it actually surprises me because like I play some of the I play some older games, and like for example I was playing this where's that game, like I was playing Mall Tycoon, and when I was looking through the files, or maybe it wasn't Mall Tycoon, it was some other game. One of the games I was playing, I was looking through the game files, and I actually saw the zlib library attached, the actual zlib library attached to the together with the game files. So meaning, and those games are like from 2004 and stuff like that. So like we know for sure that this was around in 2004, so it's probably been around since Jesus was around, perhaps. But anyways, enough messing around. Let's focus on those things here. So if you're on Windows, you actually need to I would probably recommend downloading, like you can download an installer that has everything you need. You could also like just go maybe in here, download one of those, just ignore all the anime girl stuff up here, don't worry about that stuff, it's not relevant to that. You can download the zlib stuff, and it kind of has, does it have what we need? Let's see, Windows 32. If you go in Windows 30, no, it doesn't have what we need in here. Has those? So my recommendation, I thought you could just get the what is this? Is this just the source code? Hold on. What you really need, you just need the libraries in order to compile your program. So again, this is just the same thing that we just looked at. What I would recommend doing is type zlib Windows download, and then going for this GNU Windows 32. So your GNU tools. If you get this zlib for Windows, it has a setup file, or you can just get the binaries zipped up nicely for you. You get that, and it will have all this stuff that you need to have. So in terms of libraries, so what will you need? You will need your includes. I don't know why this folder is empty. This folder is also empty. All this folder is empty. What the heck? Let's unzip it, see what's going on. Okay, well maybe don't download the zipped stuff, because it looks like they didn't include anything in here. There's the DLL file here, but you don't. I personally haven't used the DLL file. The DLL file is dynamic library, so it seems like the latest one they have here, the one that has binaries, doesn't have all the libraries. So what I would recommend, just do an installation, click download setup, and it will prompt you to install. It will prompt you to install on your computer, and then mine just suggested to install on program files x86, so I have it installed here. So GNU Windows 32, and here actually does have all the libraries I need. So it has the .lib, and it has the zconfig, and then zlib.h. That this first one you don't really need to worry about, but these two files and then this library is pretty much all you need to get your stuff done. Let me just quickly check. I actually never managed to compile it successfully in Visual Studio, because Visual Studio is just so much pain to set up when you work with libraries and header files. And what I did end up doing, I actually just ended up using GCC tools for people who are on Linux right now. They're just clapping. They're celebrating right now, because all you have to do is, if you're using GCC Linux tools, you just type GCC -M32, which is your Windows 32 option. You say which file you want to compile, and you tell the compiler where your includes are and where your libraries are. So like, for example, if I go into my work, so like, you've seen that I've saved, like, I've installed the files, all the include files and stuff like that, in a folder in the program files. Because it has such a long path, I decided to, make it shorter by putting it into a folder that has less it has less characters, and it doesn't have spaces, because when you try to compile something that has spaces, it just doesn't always work right. Give me a second here. I'm just trying to remember, because I didn't do it yesterday. I did it last week, and I already forgot how I did it. So I think at the end of the day, you don't actually need this .lib file. You actually just need the this zlibh, zlibconfig.h, and you need libz.a. Judging by the my command line, the way I had it here, so this flag up here, LZ, just stands for libz.a. So and then you should find, you have this libz.a in here, so you don't actually need this. You don't actually need that last one. So you're actually working with this three. Header files and then one library file. That's all you really need. Now, somebody who lived, 1,000 years ago, around the same time Jesus lived, they already came up with software, or they already came up with code that does stuff that we need to do, and more than we need to do. So you probably seen that my source file here is named zpipe. It's actually been written by somebody whose name is not on here for some reason. Oh yeah, Mark Adler. Again, 2005. Man, 2005. Like, that was, you know how old I was in 2005? I was 5 years old. And it's 2024 now. Over almost 20 years ago, somebody wrote this piece of code. And yeah. So if you go online, you can actually find that code on you can find it here, and you can find on GitHub, because there good people upload that stuff. But originally it's originated from this website. Again, zlib.net is this website where you can find all the information related to the zlib stuff. And somebody back in 2005 came up with an example of how to use inflate, deflate, compress, and decompress functions and stuff like that. And that's the code I'm using, because I don't have time to sit around here and try to understand how it all works. It's just easier to use someone else's code as a basis and then just modify it as per my needs. So, and that's what we're gonna do. So at some point right now, like what I have here right now is the one-to-one exactly the same code, almost exactly the same code as what we just looked at. GitHub. So yeah, like, you know, if you, it's I think it should be easier to just download from a GitHub. So you just go click on this file here, and then, you know, you just download the raw file. Here we go. You have the stuff that you need to work with. And then you have the libraries, so you're pretty much ready to compile things. However, if you're on Windows, it's actually much easier to do on Linux, because just Linux is superior to Windows. I hear somebody getting mad. Okay, wherever. You suck. If you're on Windows, you suck. You hear me? Anyways. Yeah, so anyways, so if you're on Windows, and if you're using a Visual Studio, you might run into some issues where this shit just won't compile. Because Microsoft and Windows and everybody else, they like to take things that work and they like to make them not work anymore. So in the original, there's important modifications you have to make to the original code, right here, where it says set mode and file no. This, if you're on Linux, you don't actually need to worry about this, because this whole part of the code is actually dealing with Windows issues, because the way they design Windows is that it always likes to add the carriage return and the null terminator, or what is it, like ls. They said what it was. It was like that. It's if you wanna understand this better, you just type set mode Windows. The reason I have underscore is because that's the newer version of the set mode. So basically, what it does, what it should tell you, what it does, what does it tell you? It sets function. It's certain. It takes your stream, and it doesn't let Windows modify your stream by adding carriage return and the line feed, because if Windows does that, you're gonna have some extra shit at the end of your file that you don't need, like, and it's just some people say it can even corrupt your files as well. I think it's said in here somewhere about corruption. I don't know. Anyways, so congratulations, Windows users. It's like it's a pain to deal with this in Windows, but so basically, the issue you're gonna get if you use it, if you use the original code as is, if you try to compile it, you're gonna get a bunch of errors. I changed some things around. That's why. So anyways, I'm not gonna show you the errors because I have some other errors right now that it looks for that. It's looking for that file that I deleted, but it doesn't. It shouldn't look for that file. Basically, on Windows, if you use the set mode and file number right now, if you try to compile it in a Visual Studio right now, it will tell you that these functions have been deprecated. You cannot use those functions anymore. Luckily, the solution to that problem is pretty easy. You just add an extra the underscore in front of it, and that makes it work, because underscore set mode, unlike, so the original function was set mode, underscore set mode is a newer version of that function, which has all the safety features and other stuff that you need. So, and then of course you want to work in binary mode. So basically what the program does, I'm just gonna quickly go over what this program does. It takes the it takes input in the command line. It takes the file that you are wanting to inflate, and then it outputs the file that it outputs the inflated file, right? And it does this in the by the way, this was not in the original code. This shit just wasn't working for me, so I was trying to figure out why it wasn't working. I never did end up figuring out why it wasn't working. So I just compiled it with GCC, and then it was working. So honestly, at this point, I just suggest everybody just compile this GCC again. The GCC code is, it's just literally just that's all you type and it all works, okay? And then those are just locations of your libraries and include files as well. So don't get scared by this weird Y looking symbol. It's because I'm using a Japanese version of Windows. It for some reason it modifies the slash in the Windows to this yen symbol. So disregard that. Okay, it doesn't really matter. And then so essentially it opens up the file and it streams the file contents into the stdin, and the output once it's inflated, the output gets streamed to the std out. So you're working with streams, std in, std out, and this actually does a lot of stuff. So this does a compression, it does decompression, it does inflation, and it does deflation. Now, because all we're interested in reading the data, all we do, we take this data that we gathered from our all this stuff, all this shit up here. We have to deflate it. So we don't need to decompress it. So like deflation, like this whole function here, you realistically, if you're making your own version, if you're making your own software, and you're not planning on modifying chunks, and then unless you're writing a piece of software where you're modifying chunks and then want to deflate the data again and put it back into a chunk, you can keep this function, this deflate function. Otherwise, you can get rid of it because you don't need it. I've kept it here because I'm still trying to get it to run when I compile it with Visual Studio. But you can remove that. You don't need this deflation. You don't need the deflation. You only need inflate function. You can modify it such that you don't need the this is just error reporting. I'm gonna get rid of it because this is like you know how they always say, like, most of the time programmers spends thinking about what user can do wrong, and this is the solution to that. Like, user can do a lot of things wrong, but I'm not really planning on the software I'm writing. I'm not really planning on sharing it with too many people, so I'm not really expecting to. I'm not really expecting people to fuck up. Okay, so this way I can save up on few lines of code, potentially some processing power, and it's a subject. It's a subject for consideration. So I'm most likely just gonna get rid of this because I don't want this. I don't think I need this. So But definitely you don't need stuff like deflation. So yeah, and then inflation, like this does all you need to do. Like you can write something similar to this, but I mean, if somebody already made something that works, why would I reinvent the bicycle? So I can just take this code that I have right here, and I can strip wherever I don't need. I can modify it such that I only keep things that I need, right? And everything else can go and go away, right? Again, I can't really go into here and like explain how it works, because I don't fucking know how it works. I just work here. So yeah, what does matter to us? Did I make modifications? Nah, no, don't save. What really does matter at the end of the day is the fact that is where actually did I save this? Where did I save this shit? Because you have to go now and decompile that, or I might have to go and recompile that stuff. Where was it? It was what's the folder name? Repos. Oh, I see. Repos. Yeah, let's get there quick. Where's my documents, bro? Here we go. I'm the type of user who, whenever he tries to find his user folder, he just uses update. So yeah, please don't judge me. And then from here, source repos. Where's source folder? Source repos. Don't worry about that as a folder. So release. Where is my thing that I compiled? And when did I compile it? Was this the one? Yeah, okay, so this is the one. So so basically the file that ended up coming out from this compilation, GCC compilation, was a.exe. So if I take this a.exe, and again, it all depends on how you compile it and how you name it. I take this, I'll close this, I'll open this up here. No, this has MCA. So this is the file that this is the file that we got. This is this file right here. This is the file. This just has the deflated Minecraft world save data. Okay. So now we're gonna do magic here. We're gonna open up. No, we're not gonna open up PowerShell because PowerShell sucks ass. Can open up a command prompt and navigate down to our desktop, if I can remember how to get there. No, desktop. Okay, I have to go users. GOS client. Desktop. No. Here. Okay, we're at the desktop now. So if you just do a.exe, it doesn't tell us anything. It actually gets stuck in because it was not because the program wasn't written with kind of like somebody, like there's no the program doesn't check for no input. So if you don't input anything, it actually just gets stuck. So you actually have to provide something. So you do a.exe. I think if I do this, no. Hold on, maybe I had to do something wrong for it to not work. Let's see. Okay, here we go. So now it tells us how to use it. So you have to is don't worry about Z-pipe stuff, but we have to use the -d flag, and we have to use those fucking brackets because that's the because we're using std in and std out. That's just the fucked up way of doing things. So what we do is we do a.exe, or you know, just to make it what should I name it? Just so we have a more clear understanding of what we're working with. I'm just gonna call it okay, we're just gonna keep it as A. And I think if I put A, everybody knows that this is the file that I'm trying to run. Okay. So we have to do this, and you have to put our the file that we wanna inflate, and then wanna put the file name that we wanna deflate it to. So that's not the file we wanna deflate it to. I want to deflate it to a file with the extension nbt, because once we deflate it, you'll see that our data would be written in nbt format. So I'm just gonna run this. I'm gonna do that, and boom, it creates a file. This right here. No, it did not do things right because I forgot to provide the -d flag. It actually did not. It did not inflate it. It just gave me the same file. So don't forget to put the D flag in there. Now it okay. Now it doesn't work because invalid or incomplete deflate data. Okay, we're just gonna do. We're just gonna compile it again because it looks like I didn't compile it right. Or it looks like I compiled it with Visual Studio and just didn't work really well. Oh no, did I close my command prompt? Okay, cd c user user GOS desktop. Here we go. Start from here. Because I saved this for my reference, because it's whenever you do research, people always save your research somewhere, like always write down notes and stuff, because I did it last week and I already forgot how I did it, but luckily I have a screenshot of it saved. So I want to put our Windows, because we're compiling for Windows 32 32-bit program, we have to put the M32-bit flag. So we put the name of our where is it? Did I close the Visual Studio? I'm just gonna copy this here, put it in here, boom. So now we have it on the desktop, easily accessible. Z-pipe.c, and then what else? So first, actually have to tell them where to find the include files. So stuff like .h files, right? So that would be in work includes, right? And then we have to specify where our libraries are. So it would be C work no work includes -lz. So -lz is the library that we want to include. So it's that where is it, libs.a. So that's what we're trying to include. So let's go ahead, run this, compiles a.exe. So now I don't know why I closed the command prompt again, because I'm fucking stupid or something. Let's just do it this way. Open. Just gonna cheat. CD. Boom. Okay. Okay. So a.exe flag. And then we want to do C. And then we want to put the same, no. Ah, fuck. And then I want to do NBT, like I talked about this earlier. Okay, something is wrong again. Invalid or incomplete display data. I made it work, but I also broke it apparently, because it was working fine last time, or whenever I was working on it last time. Maybe I should put this. Imagine if it's all because I deleted the wrong file. And then GCC. Do I have to recompile GCC now? Yeah, I do. And 32. That pipe. Let's see. Include C. No. Work includes L. C. Work includes dash LSD. See if it works now. Delete that file. Still gives me an error. And then if I try to open it, I think it just gives me empty. Yeah, it just doesn't work. So this I kind of spent like a whole 8 hours trying to fix this error. There's nothing wrong with the code. It's basically, as far as my understanding goes, it's the issue with the libraries and how they're all linked and stuff like that. Last week, when I was compiling this with GCC, I actually managed to get it to work, where it didn't give that error to me anymore. But it seems like this issue is back now, and it's a little harder to deal with it now that also this has way too many things here, because our stuff started with 78. No, what the heck did I copy? We're gonna redo this again, because it looks like I messed something up and didn't copy the correct things. That's it. Possibly that's why it tells us that it seems like this time I'm having actually issues with the actual file I'm dealing with. So let's go back to our chunk world here. Let's go back to our region. It was -1 as far as I remember. So 1F1, okay, F48. I just want to make sure it's the same file. Okay, so 1F 1FF000. Hold on, 1F00. Sorry. I'm starting to go crazy here. Okay, so we need to start from this point. We talked about why we need to start from there. So we start from there, and we go down. We select everything up to here. We say export selected bytes to file. I'm just gonna do all files. I'm gonna go here. I'm gonna do chunk zlib. It's already existing. I'm just gonna overwrite it. Yep. Now just to double check and make sure that I did everything right. It starts with 78 and it should end with 15. Okay, here we go. Always double check your work, because we just wasted 10 minutes trying to figure out something that I wasn't paying attention and selected way too many bytes or whatever. So now this works without any hiccups. This actually decompresses. It actually inflates. I keep saying decompresses. Actually inflates our file into NBT file, and if we open up that NBT file, we now have some readable information here. So this is where the second part begins. So the first part was more about getting to how to get to the point where we can read the world's NBT data. The second part is going to be about how are we gonna read the NBT data. Now I'm getting pretty tired here and not feeling like talking anymore. I'm also feeling thirsty and sweaty as well because education is like a workout. So this is all done. So we completed this first part. Second part would be reading all this NBT data, and we're just quickly. I'm like I said, we're not gonna do it during this live stream. We'll do it during another live stream some other time because I'm getting tired and yeah. But basically, as a starter, we'll just quickly take a look at NBT structure looks like. So you have a root tag, and you have this hierarchy structure where you have you have parents, you have childs, and all of that hierarchy is in this one file that I just for some reason decided to close. Where you at? Come back. It's all in here. It's all in here. So you have some once you see some readable words, that's how you know that you correctly inflated your file. That's how you know that you have the correct data. Now you're starting to see some patterns. So your whole file is split into the into all this information. Again, you have some alignment here going on. So you have some things. You have a lot of zeros. You have some interesting looking shapes and forms. We will take a detailed look at this later on. I should study this myself and prepare for the next live stream because I don't want to be sitting around and figuring this out during the live stream. I think it's just going to be a waste of my your time, and it's just not going to be very interesting to watch. But I got you to this point. This is pretty important to get to this point, because if you can't get to this point, because I could like the hardest part that I spent a lot of hours on, 8 hours on, not 8 hours, oh sorry, like 16 hours maybe, 2 days, I spent 2 days on, or equivalent of 2 days, 16 hours. I spent more than 2 days just trying to figure out how to take that compressed data or in deflated data. I'm just saying random stuff now. How to take that deflated data and inflate it. That took a lot of time. Took a lot of trying. Took a lot of time trying to figure out Visual Studio. At the end of the day, GCC worked. That's a good stuff. That's good stuff right there. In regards to the so if you guys are trying to compile it with Visual Studio, just make sure you have your libraries and include files set up correctly, because the way I have my things set up, it's kind of like it's wacky, so that's why it doesn't work. So but at the end of the day, if you compile it with something, if you compile it with Visual Studio and it doesn't inflate your data, just try the GCC tools. Okay, GCC is easy to install. I know some of you are hating Linux and you're like, oh no, I don't want to use Linux. Just go get yourself GCC Windows 32. That's all you really need. So you just you get your no, it wasn't up here. You just download your whole everything you need in one of those links. It's pretty easy to figure out. You know, it's doesn't take too much time to figure out. You just install it. You install it with GCC. You install your GCC. You will have to make sure your GCC is configured with your environmental libraries or variables, not libraries. What am I saying? Environmental. So you'll have to make sure that it's in your with path. Yeah. I have it set to this, but oh yeah, because it's inside of the minimalistic GW32. Yeah. So yeah, you would have to do something similar, depending on where you save it, because or depending on where you keep all your libraries. Like in my case, all my GCC tools are in here for the 32-bit version of Windows. And you'll see that GCC is in here as well. If you're like me, who programs in 64-bit assembly, I also have a 64-bit libraries for the assembly whenever I assemble things together. But I'm not gonna be using assembly for all this stuff just because it's I don't have enough hours to work on this. So what else should we discuss? So I hope this 2-hour lecture live stream 2-hour lecture was it's a bit too long, but maybe at some point I'll compile like a small video where a smaller video where it's nice and easy to follow the information, instead of have to sit here for 2 hours and listen to me talk and try to compile things that don't work. But today you get to experience me compiling things. Today you get to experience me troubleshooting things, and hopefully this helps you on your journey to like when you're gonna have troubles compiling things or issues with things. Hopefully you'll know how to resolve those issues pretty quick. Hopefully you'll know how to troubleshoot those issues. Take a look at this, and then I'll see you next time, and we'll take a deep dive look into all this stuff, and we'll figure out how it works. We'll get to that sign. We'll find where that sign is. But you actually might be curious right now if we can find that hello sign right now, because it's just hello. Should probably be stored as a string. So let's try that. Let's see if we can find hello. No, it's not easy to find. So it's probably saved as ASCII character, but it probably has some formatted strings, because you know how you can have Minecraft formatting. You know how in Minecraft you have formatting codes like this? Where is it? Yeah, like all those formatting codes where you can modify the color of things, books, signs, and stuff like that. I bet it's possible that the way the data is saved here, it's not hello, it's probably something like hello, and then it's this weird symbol up here, and then I'm just gonna put like a $sign, something number, something number, something number. So it's probably formatted in some way. That's why we cannot find hello. So that's why we'll have to dig this down, starting from the root tag, digging down all the way down to wherever that sign might be. I have no idea where it might be, but we'll figure out next time. So until then, I hope you had a good time. I will see you next time. Bye bye now.